Okay, a few more antiderivatives for us to deal with here. These are a little more complex, but we do have substitution, so we can probably prevail anyway. This first one contains 5x minus 3 to the 12th power, and you could brute force expand this, or you could expand it using the binomial theorem, I guess, but man, a lot of work and a lot of opportunities to make mistakes, so preferable is to make a substitution, and I would suggest we use 5x minus 3. Everything inside the brackets can be our u. And then our derivative will simply be 5dx. And if you like, you can divide both sides of this by 5 and get 1/5 du equals dx. So, having established all that, we can rewrite the integral now. Instead of 5x minus 3 to the 12th, I'm going to write u to the 12th. And instead of dx, I'm going to put 1/5 du. I'll put the du on the tail end of the integrand, where it normally sits. The 1/5 I'm going to put outside the integral because you're allowed to do that with constants, and why not? Okay, so now this looks like an antiderivative we can do using the power rule. Our 1/5 just sits there waiting. The power of u increases by 1. There it is, 13. And then we divide by the new power. And we can squish these two fractions together to get 1/65 u to the 13th. And there are two reasons why that's not a good finished answer. Do you see what they are? First, they gave us this question in terms of x, and we're coming back with an answer in u. That's not good. When you've done a substitution, you should revert it at the end. So instead of u, I'm going to put back the 5x minus 3 now. 1/65 of, it used to be u, but now we reveal it's actually this, to the 13th power. And the other thing, I'm probably not catching you with this anymore, don't forget your plus c. Okay, over here, radical of polynomial expression. I'm hoping there's a relationship between the 4x squared minus 10x and the 4x minus 5. I'm hoping that if I differentiate this, 4x minus 5 falls out somehow. So let's try that and see what happens. If we make our u the radicand, 4x squared minus 10x, and we differentiate that, we get 8x minus 10 dx. Well, calamity, there's no 4x minus 5 involved there. Or actually there kind of is, right? Because if you factor a 2 out of this, du is actually 2 times 4x minus 5 dx. So clearly they've been cooking. They mean for du to replace this part. There's an extra factor of 2, but we can live with that. A little constant out front isn't going to hurt us. So let's see if we can get this fixed up. Instead of 4x squared minus 10x, I'm going to say u. So we have root u. Next line, I'm going to start writing this as u to the 1/2 because I feel like the power rule is sneaking up on us, but we'll get to that in a moment. Now, I want to replace 4x minus 5 dx. If I divide both sides of this by 2, that would be pretty nice, wouldn't it? That would be a perfect match for what's actually in the integrand. So if I divide both sides by 2, I get 1/2 du equals, that 2's gone now, 4x minus 5 dx. So that means all of this I can replace with 1/2 du. There's the du, there's the 1/2, and now we pretty much got it. 1/2 integral u to the 1/2 du. The 1/2 just sits there, and when we do our antiderivative, the power goes up by 1, and then we divide by the new power, which is the same as multiplying by the reciprocal of the new power. So there's our improved function, and plus c, of course. When we multiply these together, the 2's cancel, so we get 1/3 And I was going to say u to the 3 over 2, but let's switch this back. I'm doing these steps a little faster, partly because you've seen them a couple times by now, and partly because I'm running out of space, to be honest. So there's our, oh, I'm sorry, 3 over 2, not 1 over 2 anymore. And, of course, plus c. You could rewrite this as 4x squared minus 10x to the third power and then put a square root sign on it also. If you aren't fond of the fractional powers, that works, but I think I'd be inclined to leave it just like this.